Hello everyone, and welcome back to ADAP, our course on Advanced Design and Programming. We are now leaving the programming level and will focus more on the design level. So the first topic, or today's topic, is design patterns. To understand the concept of design patterns, we will start example-driven and then work our way towards the abstraction called design pattern. We recognize how there are multiple levels of abstracting and summarizing design experience, which is what design patterns are about, and then turn around and take a look at how to describe patterns, how to apply them, and how to embed them in your design process. Let's start with a couple of examples. So I will first talk about the classic file system hierarchy, so directories or folders and files, and how to design that. If you start out and your task is to provide or develop an object-oriented model of a directory structure, folder structure, it might look like this. You start with a root directory, and the root directory can have directories inside of it, can have files inside of it, and it might have links to other elements of the file system, like the root directory itself or other directories of the file. Directories can contain directories and, of course, files. So you can see that here in the UML diagram and in the associations between them. So, for example, that a directory can contain subdirectories or child directories here. You can see that by the relationship from directory to directory itself. And that is a reasonable first example or first take at designing a file system structure. You could do it differently. So you could recognize how the root directory is just a special version of directory and could be therefore a subclass of directory. So you turn it around or you make root directory a subclass of directory, but you still keep links and files. One simplification is that the link now only links to directory and file, and the root directory being a subtype of directory implies that the link to directory also works for root directory. Still, that is not quite satisfactory. You could make one further step of abstraction where you realize that all of these elements are actually nodes. You're looking at a tree structure, and where then the directory objects are the intermediate nodes in that tree structure, and files and links are the leaf nodes of a hierarchy, file hierarchy or directory structure. So that then leads to an abstraction called node with three subtypes: link, file, and directory. And here it comes, directory containing not just other directories, but just any node, including links and files and, of course, further directories. So the containment of what is in a directory, which used to be all these different elements before, explicitly referenced from a directory object, now they have all been sorted under node as a superclass, and hence directory only needs to have as child objects nodes, which then can be links and files and directories. So straightforward. The interesting or the key design decision to realize is that combination of directory being a subclass of node to give us the intermediate nodes in a tree structure, and directory having as elements any form of node, including itself. So there's the recursive structure between directory and node, which makes this a good way of representing a hierarchy or a tree structure like you would need it for modeling a file system. In class, we would usually now run a simple or fun example of traversing the tree, the directories tree, and running an algorithm by counting the size of all elements in there to derive at a total size of the folder structure at the root, which would be 2484 bytes, or maybe more kilobytes then. And that is a good example of realizing a tree structure using the files for a file system. Now let's switch examples and go into the financial services domain. So if you are a bank, you want to know how much assets you're holding in your trading division, for example, where assets are so-called financial instruments. Basically could be stocks, could be all kinds of things, financial objects that cost money and that are worth something, like bonds or stock and what have you. The bank always needs to know how much money is at risk if something really bad happens, like a stock market crash. So one way of modeling it is to have the whole exposure of the bank modeled in a tree structure, because by organizational unit, by person, by customer, to some extent, you already have a tree structure in this scenario where you have the overall portfolio of the exposure broken down into sub-portfolios, broken down into sub-portfolios, and so forth. And so as you might model it here, whatever you have is a position, and then a position is part of a portfolio. So you can see the class portfolio holding positions, but one position in the portfolio or multiple can themselves be portfolios again, and that way you establish a tree structure of portfolios containing sub-portfolios next to all the specific financial instruments that are available. And you might recognize how this is again a tree structure, and where the key design decision is the relationship here between position and portfolio, but portfolio inherits from position, and portfolio also includes at runtime further positions. And now for a third example that might be more familiar to you if you're using unit testing framework like JUnit. When you look at how your tests are organized, if you've ever looked at it, then you will see that you program all these tests, and JUnit, when it starts up, creates a tree of tests where there are the individual tests. So a test case class gets instantiated for each test case in there, and then the test case classes tests all get assembled in one test suite. And then a test suite can contain further test suites. And again, you're building a tree structure, which at the root is a test suite object, which contains further test suites and further test suites and further test suites, until over the leaves then are specific tests. And when you look at the design here, again, you can see how test suite is a subclass of the more general test interface, and where test suite also contains all kinds, can contain tests, some of which again might be test suites because of that subtype relationship from test to test suite. So what we have now is 3 separate design examples of how to model a tree structure, and they all ended up, or at least that's how I present it, with a key design decision of having a node class for any element in the tree, and then a subclass of that node, which is a directory or a portfolio or a test suite, just a composite node, meaning a node that can contain further nodes. And you model that by making the composite node just another node, so it's a subclass of node, but at the same time what's special about it is that it can contain, by way of an aggregation, further nodes. So these are the two relationships, again, the inheritance and then the aggregation. And that is, these three examples are an example of the composite design pattern. So what is the composite design pattern? Well, it's in the words of the originators, it is design pattern is experience that has been turned into a structure that can be used and reused by way of application over and over again. It's distilled design experience of how to solve a particular, how to solve a design problem well and repeatedly well. And then design patterns are described using various forms, and since design patterns were coined as terms in a particular book called Design Patterns, we are first using the form of that book, which mostly consists, not only, but mostly consists of the so-called structure diagram, which is something that looks like a class diagram. And for the composite design pattern, you can see the composite structure diagram here using its original drawing, where you have component, which is our node in the tree, and composite, which is the subclass of the node, the composite node class, which is both a node, so it can be contained inside composite nodes, but also can contain further nodes, including other composite nodes. So this is an old school notation, OMT, it's not UML, and this funny triangle between composite, leaf, and component indicates an inheritance relationship, and the children's link is the aggregation that we already know. So we have a particular design structure here again, where there's a node class or called component class here, and a subclass of that node class, which is for all the nodes in the tree that can contain children, and that children ability is modeled as that link back from the composite class to the component class. And then you have example operations here for building the tree. For example, the node class or the component class has add and remove operations for adding a child object and removing a child object. And then here something called operation, which is a placeholder for the specific functions you need when using the design pattern in a specific design. That is a key insight. This is a general idea being displayed here, and you always apply it in a particular context. So for the file system example, the operation would be get size and get size of tree, meaning you would iterate over the tree with respect to get size of tree to compute the total disk space consumed by that tree. And the operations are defined in general on the node, and then they get specific implementation in the composite subclass, because that has special meaning because it's possibly going to iterate over all the children. And it has a different implementation in those component or node objects, classes for those objects that do not have child objects, no children, but that are basically the leaves of the tree. And this applies to the portfolio example, and it applies to the TestSuite example. So let's use yet another example to drive home that design patterns always require multiple examples before you can make the claim that something is a generalizable solution to a problem. And let's pick something close to home. You're configuring a computer which consists of parts. Some of these parts are atomic, meaning they are leaf nodes. And some are composite, meaning they're intermediate nodes that are built from more nodes. For example, the memory subsystem takes all these memory banks. The storage subsystem may take multiple disks, what have you. The video subsystem might take extra chips that you can plug in, etc. So, using the composite design pattern, how would you design a class hierarchy to represent this computer configuration? So, which of these makes sense? Each type of atomic part is represented as its own class. Each type of composite part is represented as its own class. All part classes are direct subclasses of an abstract part class. What do you think? Think about it for a second while I wait for it. All right, I hope you pressed stop and thought a bit so that I can go on. Well, here is one way of doing it. You just have a lot of leaf classes, the atomic parts, so keyboard, so some atomic parts, even with specialization still. So there's keyboards, which could be specialized models. There are memory banks, which also have specialized models, maybe a bit getting older here. And of course, you have the composite parts, which are built from multiple components, and you could have those modeled as the different subsystems modeled as composite parts. You could do that, and that is a reasonable way of applying the composite pattern here, which you can see is applied to have part and composite part, which gives us this key structure of managing child objects here called subparts, while the composite part itself can be a subpart as well. And here are the detailed answers. Yes, each atomic part is its own domain concept, composite part is its own domain concept, but you do want that intermediate composite part class, and but you will not put everything under an abstract part class. So we now looked at 4 examples of designs, or 4 different designs, underlying which was something called the composite design pattern, an abstraction from recurring design solutions that just make sense and that are similar in this particular respect, that you have a node and a composite node class, where a composite node is a subclass of node but can also contain nodes to build the tree structure. And so the composite design pattern itself then is an example of the concept of design patterns. Or it is a design pattern. So then, a design pattern is the abstraction of a common solution to a recurring problem for a given context, and the composite design pattern is an example of such a design pattern. And obviously there are others. For fun, here is what is not a design pattern. So the German term for design pattern is Entwurfsmuster. This was asked on an exam. A simple or a single class like hotel is not a design pattern. A function on a class is not a design pattern, and so forth. Why would you care about design patterns before we continue on to further examples? Well, the benefit of understanding these designs, which capture time-worn, well understood solutions to recurring problems, is that you can use them over and over again. And if they've been described right, they are so flexible that each use allows you the variation necessary to solve the specific problem at hand. So you use design patterns to capture experience, communicate that experience, so that you or that others can then use that experience in the design of the software. Doing so, design patterns give us a common language to talk about it. They give us the terms by which we recognize that design experience and more efficiently can talk about it. If you didn't know that the composite design pattern existed, and you didn't know that it has these components called component and composite, then you wouldn't know these terms and you couldn't communicate with them to other people. But now that you do, and those others do as well, because you've all read the design patterns book, within a few words you can say, oh, I recognize how portfolio and position is really probably best captured as the composite design pattern. So let's make portfolio the component, the composite class, and position the component class, and off you go. Because everyone in the team who is knowledgeable about design patterns and these design patterns recognizes then what needs to be done. So understanding design patterns helps you in the design of software, in its documentation, and as you go about the design by communicating it to other people in the documentation or in front of a whiteboard as you're working on design solutions to your challenges. And so again, there is the original design patterns book by Eric Gamma, Richard Helm, Ralph Johnson, and John Flicides from 1994 or 1995. There's a German translation, though I think it's not available any longer. And you can, I recommend now these days, you read the English original. None of this came purely coincidental. On the one hand, this particular book was a big success, was a breakthrough, but it also happened in a culture in the 90s where multiple people were working on design patterns and where there were various precursors. So first of all, the notion of a pattern as recurring solution, abstraction from recurring solutions to problems in a context, was before software recognized already and codified as such by a practicing architect, Christopher Alexander. So that was not a software architect, but a building architect who wrote a book called A Pattern Language. His idea was that these patterns exist, not just in software. He didn't think about software, but in the design of buildings. So he would have patterns like light from two sides. There should be no room which only has a light from one side. He believed that each room needed to have lights from two sides. He wrote 250 something patterns like this that ranged from the design of whole cities down to the details of an apartment and individual rooms in there. Another important thing going on in the software world now, we're switching from architecture from the 60s, 70s, and 80s to object-oriented design in the 80s and 90s, was the observation that no object is an island. When you think about object-oriented design, this statement by Kent Beck and Ward Cunningham recognize that objects interact. Designs are always in the interactions of objects. So you can't just look at one object, not just look at one class as an implementation of the object. You have to look at the interplay of the objects as defined by the classes, which is where the creative or where the design solutions in the design patterns book came from, because while it's possible to have design patterns that center on one class only, almost all of the design patterns in the famous design patterns book are about how instances of different classes interact smartly to solve a problem. So it's about the collaboration of classes. In the run-up to the design patterns book, there were some software frameworks on which the authors of the design patterns book worked. Most notably Eric Gamma and Andre Weinand, who worked on ET++, an early C++ framework, application framework for building applications at a bank, at UBS back then. And then there was John Flicidi's work at Stanford on interviews, an early C++ user interface library. Back then, when there were no simple object-oriented wrappers or object-oriented user interface libraries. So these people gained much of their practical experience from the implementation of these systems, and that's where they recognized certain well-working designs, and that's where they, when they talked to each other, recognized that they had found similar or identical solutions to recurring problems that they all had to solve, and hence the idea of design pattern emerged. I don't think that these authors originally knew about Christopher Alexander, but they quickly picked up on the idea of pattern and then turned their hard-won lessons about good design into design patterns in the Design Patterns book, which originally was called the Design Patterns Catalog. And so they worked hard to gather all this experience, distilled 23 distinct patterns into descriptions of 3, 4, 5, 6 to 10 pages each in this particular book that created the energy behind the design patterns community for 10 and 15 years. Another relevant book called A System of Patterns tried to find more patterns, so there are always more patterns, but not just catalog them, but also not turning them into a language, but turning them into a system. Christopher Alexander's original language idea was that you could basically start a sentence, human language sentence, use the terms from the patterns, and by speaking that grammatically correct sentence, ultimately have designed a house or even a city, etc. Might be a long sentence then, but the patterns fit to each other as if you were speaking a language. They were so flexible, they were so easy to use building blocks that you would form sentences that made sense and were grammatically and semantically correct. The System of Patterns folks, mostly from Siemens out of Munich, concluded that a system is better. And so they had a notion of structured dependencies, etc., which went beyond the Design Patterns Catalog, which just defined specific relationships, but no system of relationships. So if these are design patterns, they are obviously not specific designs, but they are abstractions from designs. And so I find it helpful to distinguish the various levels of abstraction we find here. So first of all, the Design Patterns book, which triggered so much interest in codifying hard-won experiences in an abstract, more easily usable format for application in different contexts. They focused on object-oriented design. So designs on a certain level of granularity involving 2, 3, 5 classes. And that's the level of granularity. Arguably then, people started talking about patterns above that, most notably architectural patterns or architectural styles. And that are also patterns, just not described using classes, but maybe using an architecture description language or an abstraction thereof. And these architectural patterns would capture how to design the architecture of a software system. So for example, having a layered architecture would be a way of structuring code dependencies between layers in a large system. Or pipes and filters would tell you that your system could be built as a sequence or a graph of pipe objects that attach filters or components with each other that do some processing on the data that comes through the filters, like in the Linux command line or Unix command line. Those architectural patterns of granularity level, arguably that's larger or more coarse-grained or bigger than design patterns. And so we can also look into the other direction, into the implementation of classes, where we will find something called programming idioms, which are patterns of how to program well. Arguably, you've seen some of those in my discussion of the various method types, the interplay between these methods, and these are programming idioms. They are not full-blown classes. They structure in the small, using well-understood patterns of how control flow happens in programs. And so let me go over that with a little bit more examples. An architectural pattern is a publish-subscribe architecture or event bus. So basically a software architecture where you have components that communicate not by method calls on direct dependencies, but by registering their interest in certain events on some sort of bus, and then also publishing events if something of relevance happens to that same bus. So any component hooked into a publish-subscribe architecture could be a publisher, could be a subscriber, could be only one of them, could be both, and communicates with other components in a decoupled way. A publisher does not know who subscribes to their events, and a subscriber does not know what publishers there are and does not subscribe to a specific publisher, but only to a specific type of event. This way you get a loosely or more loosely coupled architecture than you would get if you had direct dependencies between those components. So it has the property of a looser coupling between components than a regular architecture would give you, and is therefore more flexible. You can more easily attach new components as publishers and subscribers. And as you describe such a pattern, we've established over the years certain patterns of how to do it well. And one key aspect of it is that if you claim you have a pattern, you should provide at least 3 examples. That's a heuristic, the rule of 3. For everything you claim that it is a pattern, you should have at least 3 well-matching examples. Otherwise, you can't quite claim that it's a pattern. You might claim it's a pattern in gestation or a proto-pattern, but it has not been shown to be a pattern yet because there are not enough well-known matching examples. Here's an example of a programming idiom. So that is the one I usually use so that we all know. The get, next, and increment function of an iterator usually. So it often goes together that you are iterating over something, you want to know the current element, and you want to be ready to get to the next element. So you move into one method rather than keeping it separate. You move into one method, the get me the current element functionality, and the increase the pointer of the current element to the next element after you returned the current element. So all iterators do something like that, and that's a well-known idiom. It's so well-known that it, as mentioned several lectures ago, violates the fundamental principles of good method design. Only have a method do one thing, but that is exactly all right to be violated if you follow an established idiom that has a specific purpose like this get current and advance programming idiom. So we looked at these granularities levels of abstraction. There are others to be talked about later. We talked about the composite design pattern, but by looking at these other coarse levels of abstraction, we already recognize there are obviously other patterns, and in the design patterns book there are 23 of them. So the original design patterns book description hasn't quite stuck. It was actually very well done from an educational perspective. John Flicidis put a lot of effort into communicating and writing this well. But it is very much object-oriented and maybe too much, and most pattern authors these days will prefer a simpler solution or a simpler template for describing and capturing patterns, which focuses exactly on the 3 core components that you would want to have, which is a description of the problem the pattern is trying to solve, an elaboration on the context where instances of this pattern could be observed, and then the actual pattern in the form of a solution to how that problem in that context is solved. Please note that while I may appear to be speaking about specifics, like when I say the specific context, but I'm always talking about the abstractions from the specific situations. You want to go beyond the context of that particular system, but this type of system. You want to talk about types of system. And then you don't only want to talk about particular types of systems, but really understand the so-called forces that may be at play. And the challenge of a good description is, how do you make that abstract so you're not overly constraining the applicability of your pattern solution? How do you make that abstract and it still communicates and is not just too general? That's the constant challenge of writing design patterns, writing patterns well. In the original design patterns book, the core to most of the design patterns is the structure diagram, which is some sort of placeholder templatized diagram of how an application could look like by example. So most people will turn to the visual of some sort of class-like diagram. Here is how it looked like in the original design patterns book. Well, there was a CD, and this is a screenshot from the CD, but it's the same content as in the design patterns book. And again, it's a composite pattern where here you only see the motivating example, not the generalized structure diagram. So here's yet another example for the composite pattern, where a picture is a composed object composed of individual graphic elements, which could be pictures inside that graphic element, but also the leaves like a line or a piece of text. As you have many of these design patterns, you need to organize them as you put them together. I already mentioned how Christopher Alexander, the building architect, had an idea of pattern languages. I mentioned the Siemens folks, they had an idea of systems. And so let's look at increasing levels of specificity here. Let's start with pattern collections as loose collections, then handbooks, and then languages. The design patterns book in the inside cover has this diagram. These are the 23 patterns and boxes, and then there are links between these boxes, where the links are somewhat ad hoc relationship descriptions. So the composite pattern, which you can see is quite central, it has relationships with many other patterns, but the composite pattern, for example, uses the iterator pattern to iterate over its child objects. That's the nodes below the composite object, or the components below or contained by the composite object. That's why there's a link here from composite to iterator called enumerating children. And so this is basically a collection, a catalog as it was originally called, of design patterns with somewhat loose relationships and sometimes no relationship, like proxy. Upper right corner isn't linked to anything. And going back here, pattern handbooks then will try to organize the patterns into categories So similar types of patterns come with each other, so you can see the relationships by the way the handbook is organized, as opposed to just all of them being flat, linear catalog. And pattern languages, as also mentioned in the beginning, tries to give you whole full-blown vocabulary for speaking about designs by using the terminology from the patterns in your language as you design a system. So there, usually in a pattern language, is a progression of some sorts, usually from large to small, turning the relationships between the patterns and the language into an acyclic graph, where you start at the top or at the largest level or wherever you want to start, and then as you apply, you go down into more details. So there is implied a top-down design technique. So when applying design patterns, what that means is you typically take a look at the design pattern description, because maybe you realize that could solve your problem, but you don't know it by heart. So you turn to that description and then you apply that description. The most common way is to simply look at it, use your brains, and implement it. Meaning you look at the design diagrams, so in the design patterns book, the structure diagram, and you kind of copy it in you apply it in your mind to your domain and copy it into your code. You could also have an existing template that you really copy and paste. So in the simplest sense, the design template would be existing code where you just adjust existing code. If you go to Stack Overflow and copy an algorithm into your code base, which you absolutely should not do, because the Stack Overflow code license is a copyleft license. But if you were to do that, you would be taking a template and adjusting it to your needs. So you don't write all the code yourself, but rather you reuse a specific form that already conforms to the design pattern, but has been applied to a specific programming language, for example, and then you just only adjust it to your needs. So it's copy and paste with adjustment. And sometimes you can use the programming language or the libraries, where there often is a connection between libraries and some programming languages and the language, which is extended by the libraries. Basically, some of the design patterns are effectively features in some languages. Most notably, what's the visitor pattern in the design patterns book is available as double dispatch in some programming languages, though not Java. So to go over this in a bit more detail, and we need to understand that, again, a pattern is an abstraction and hence is separate from its instances. So at a minimum, there's a pattern, and then there are all the instances. Some of the instances are the original instances from which the pattern author derived the pattern by way of abstraction. But usually we take the pattern and instantiate it to solve our specific problem. The pattern, there is no language for describing patterns well yet beyond prose. People have tried to come up with formal notations, but largely failed. There are, however, languages for the specific instances of a design pattern as it has been applied. For example, UML for class models and Java for programming language, for program code. Because the instance is always specific. It's a specific modeling language, it's a specific programming language that you use, so you have a language for that. Again, for the pattern, we do not have that. When you look at the design patterns book and you look at the structure diagram, what you're seeing is not a class model. You're seeing some sort of weird placeholder template model. When you look at the composite pattern structure diagram, you will see component and composite, all right, and then leaf. There in no good instantiation of the pattern, there is always exactly one leaf class called leaf and one composite class called composite. You'll always have many different leaf classes like link, file, and direct and link and file. And composite would be the directory class. So the instantiation pushes away the placeholder elements, replaces them with something specific to the problem at hand. That also means, and that is in tune, as I say, that with the authors of the Design Patterns book, that also means that there's a clear distinction between the design pattern as an abstract idea that can be applied in very different modeling languages and programming languages, and the ultimate instantiation, of course. But in between instantiation and the design pattern, we can have something which I call design template here. It's not as abstract as a design pattern. A template is always specific to the language, a modeling language, so it's either a Java template or a UML template. But it has not been instantiated yet. However, because it's a template, the instantiation follows formal rules. So it could be that you use UML facilities or some additional tool which has an instantiation algorithm that takes the placeholders, asks for a bit of piece of data, fills in that data into the template, and instantiates the template. This also allows us to deal with the variation in the design patterns. Design patterns, again, have been deliberately designed to be abstract, leaving room for variation in the templates, not only in the instantiation, but also in possible templates. So here you see 3 examples of templates for the same design pattern, the composite pattern, where each of these templates is a proper representation or proper templatization, turning into a template of the design pattern, and yet they are different. So on the left you see the classic example. Component has a subclass called composite, and composite can contain objects which are components establishing the recursive relationship to build a tree. Another way of casting it is to do away with the composite class and merge it into the component class. So you could have just a node or component class which can contain further objects of its class or subclasses. So then you just have nodes containing nodes, like in the middle here. You did away with the composite class and it's still a valid tree you can build. You may think the design to the left is nicer, but not always do you need that separation of the classes. You can also have a node class which manages contained objects in a separate group object, which is not a subclass of component or node, like in the rightmost example. Sometimes you want to handle those contained objects as its separate group and still build a tree of component objects. So the context description of the composite pattern allows for these 3 variations to all be valid templates for the specific instantiations into specific programming languages. That's why attempts at formalizing design patterns have failed. You cannot capture this broad variety using one formal modeling language, but you could use a formal language to describe the templates and instantiate the templates. This distinction between design patterns, design templates, and specific instantiations is important. The design pattern has been defined. Design patterns have been defined to be broadly applicable and ultimately not formalizable in the great degree of how they are abstract. And so you need something in between, like design templates, to give you formalizable structures that can be instantiated or applied in an automated way. But but therefore must lose some of the original flexibility of the design patterns. And then you have the final instantiation, the running code of a specific model. There's even yet one more abstraction level, which is that the specific implementation can add even more to the design. So for example, you can have additional classes dealing with code inheritance and so forth. And so there's yet another level of how a specific instantiation can get further away from what you might naively see in the structure diagram of the design patterns description in the design patterns book. All right, so back to one example we had before. You are still designing your system for putting together computers. So you have a class diagram here, and you see classes like keyboard part, memory subsystem, graphics card. And when you see these classes, what do you think you're looking at? That class diagram, is that a design pattern, a design template, or a specific implementation or specific design? What do you think? Well, 3, 2, 1, stop. Okay, let's keep going. Well, it's not a design pattern because this is way too specific. Hence, it's also not a design template because it's concrete classes. It's a specific design and implementation as given away by the names, by the really specific names, keyboard and so forth, as they apply to that particular application of perhaps the composite pattern in the design of a computer, in the design of a system to put together a computer, a custom-made computer. Let me give you some more examples of design patterns. Here's the Singleton pattern, which you should know from Wald's side. The factory objects, which is yet another pattern, the abstract factory pattern, exist only once, and that's the Singleton pattern. And how to do that, you do using specific code. Here you can see it's a static instance that gets instantiated early on and only once and not repeatedly instantiated. Therefore, you make sure there's exactly one instance of this class, which is the idea of the Singleton pattern. It will always be the same object that you request services of, and hence, as the class knows that there can only be one instance, you can program it accordingly. In the implementation of the Singleton pattern, there are challenges. So, for example, if you can't statically instantiate the factory here with instance equals new photo factory, but you have to delay that into the getInstance method, you run into the problem with concurrency, that there could be two clients calling getInstance at the same time, and they would then get separate instances, which is exactly what you do not want. You want only one instance. So you need to synchronize for that, and that can go wrong badly if you don't do it right, and because of modern concurrency. But here's one solution, and you can look up at the problem. You can look up the problem under the name of the double-checked locking, and the double-checked locking pattern is broken on the web. Finally, design patterns over time either become language features or could become language features. Sometimes they're already there, and that means that some of these elaborate designs from the design patterns book, and the key example is the visitor pattern, is simply present in a very easy way in a given programming language. So it's always the same example where double dispatch is possible in CLOS, the Common Lisp Object System, where basically the dispatch happens on the types of the arguments, of multiple arguments. 2 arguments in the case of double dispatch, multi-dispatch in the case of multiple arguments, And what that means is that the types of the 3 arguments are taken, and in that multidimensional space, that most specific method is chosen that fits those argument types best. And if you can't do that, because in Java you only have single dispatch, you apply something like the visitor pattern here, where you realize the double dispatch as a 2-step process of first and then second dispatch, first on the first argument, then on the second argument. For homework, you will look at your code and you will annotate design patterns in your code. So it's very straightforward. You look at the design patterns in the design patterns book, and you use the names from the structure diagrams and annotate your classes accordingly. Here's an example that you should take a look at to know what to do for the homework. And here is, for example, how you could specify a design pattern. First box, design pattern named Composite, has participants component and composite and so forth. And here you assign it to class node in the directory example, where you're saying the node is the component participant from the composite pattern. And for the directory class, you would say it's the composite participant from the composite pattern. And that's it from me for today. Thanks for listening on this lecture on design patterns. There's much more to say, but maybe some other time. Until then, be safe and see you in the next lecture.